Hello, this lecture begins our discussion on Fourier analysis, which is found on chapter 11 in your textbook. I'm spending time on this because it's an area within electrical engineering that's used a lot in signal processing and forms the basis for a lot of analysis in signal processing, communications, as well as other areas in physics, including harmonic oscillation and things like that. So, Chapter 11 discusses several aspects of the Fourier transform and Fourier series. We won't discuss them all, but we will point out several important parts. So first of all, to discuss the Fourier series, we need to define what is a periodic function. Basically, a periodic function is something that repeats itself, and it's defined for all real x except possibly at some specific points. So one example of that would be the tangent of x, which, as we know, goes to infinity at multiples of 90 and minus 90 degrees. But because that only occurs at a specific number of points, we can still define that as a periodic function, even though there are specific values of x for where that would not be specifically defined. So the graph of a periodic function is shown here. It doesn't have to be necessarily sinusoidal or cosinusoidal, as long as it does repeat. And so we can see here that this repeats with a period of p. Typically in electrical engineering, x is actually time, and so we're looking at a temporally repeating signal, but x can also be space, and it can even have periodicity in 2 dimensions. So for now, we'll just work with the variable x, realizing that that's a generalized variable that can take on any number of units. So if f of x, this function, has a period of p, then it also has a period of 2p, and in fact it has a period of np. So these are referred to as harmonic functions because you have a number of periods contained within a single function, and you can easily see that if we go back to the previous slide. You can see that there is a period p. There's also a period 2p, and on up to np for any integer n. So initially, the thing that makes sense is to discuss sine and cosine functions. Sinusoidal and cosinusoidal functions, along with a DC term, form the trigonometric system. And so that's what we'll start with in our discussion, because that's probably what you're most familiar with. And we'll first simplify and say that our functions are going to have a period of 2 pi. Now when we look at a function cosine x, this is actually cosine of omega x, where omega is radians per second. And so in this case, omega would be 1. To find the period, you would take 1 over the frequency. To find the frequency, you basically would take 2 pi times omega. So the frequency here is, you would take omega over 2 pi. So the frequency here is 1 over 2 pi, giving a period of 2 pi. So if we look then at what our trigonometric series looks like, it looks like this, where we have cosines and sines with integer multiples of x. And so we could write that abbreviated as the sum, where we have some coefficient cosine nx plus another coefficient sine of nx, n running from 1 to infinity, and then this a sub 0 term, which represents a constant term. Now, if we can write an expression such that the series converges as n gets large, then we say we have a function that has a period of 2 pi. Now, let's suppose that we do have a function that has a period of 2 pi. It's possible, given this, that we can solve, if we know the exact function of x, we can solve for the coefficients a0, an, and bn by the following integrals that are known as the Euler formulas, and the coefficients are known as the Fourier coefficients. This is proven by taking the general formula, multiplying by either the sine or the cosine of mx, and using the properties that sinusoidal functions are orthogonal basically what happens is you can do a derivation that causes everything to drop out except these terms shown in the integral because of the property of integration of orthogonal functions over a period. So we have these formulas that allow us to solve for the coefficients. So as an example, if we look at the rectangular wave here shown has a period of 2 pi. It can be written as the following expression where f of x is equal to minus k for x between minus pi and 0, and it's equal to k for 0 and pi. So, and then it repeats, so f of x plus 2 pi is equal to f of x, and in fact f of x plus n pi is equal to f of x. So we can find the coefficients here. First of all, if you, let's go back a step. If you look at this function, we can see that if we integrate the function from minus pi to pi, which is our range, that basically the left-hand side and the right-hand side of the integral will cancel out. So our a sub 0 coefficient will be 0 because the areas under the curve cancel each other out. Now if we want to find a sub n, we take 1 over pi times the integral from minus pi to pi of f of x cosine n of x. Doing that integration, you find that that cancels and becomes 0. Then solving for the b sub n coefficients, which is f of x sine n of x, you find that the solution is not 0. In fact, the solution comes out to be 2k over n pi times 1 minus cosine of n pi, which is just a kind of a fancy way of writing all of this. So since the cosine of n pi is equal to minus 1 for odd, and the cosine of n pi is equal to 1 for even, and we have 1 minus n pi, what we find is we only get a non-zero term for odd values of n. So all of the sine terms are going to go to 0, the constant term will go to 0, and what's left are only odd terms that are coefficients of the sinusoidal terms. So if we were to write this expression out, it would look like this, where here's our 4k over pi, and then this is our 1 over n term, and here's our sine n of x. So this is an example of a Fourier series expansion. Now notice that this term here is 1 over n, and as we get larger and larger in the series, we're multiplying by 1 over n. So we can see that as n gets very, very large, the term is going to go to 0, so the series does appear to be convergent. Here's an example of that series where we have the first term, we have the first 2 terms added together, we have the first 3 terms added together, and so you can see we're slowly building a square wave. Now you know from electrical engineering, your electrical engineering background, but as a general rule, you need at least 3 and typically 5 terms in a Fourier series to really approximate the waveform that you're trying to construct. The number of terms in the series increases if you have sharp edges in your waveform, and the sharp edges give rise to this ripple effect that you see in the Fourier approximation of the waveform. This is known as the Fresnel effect, and you see this, the greater the number of coefficients, the higher the frequency of the ripple. So this is just basically saying that if we set x equal to pi over 2, we get a value of the sum of coefficients that's equal to pi over 4. Just kind of an interesting aside, not really something that we're covering this semester. So the trigonometric system is orthogonal, meaning that if we take the integral over a period of the cosine of n pi cosine of m pi, that's equal to 0 except for when n is equal to m. The same is true of the sine, as the same is true of sine cosine. So this is one of the ways that the coefficients are determined. Basically, a Fourier series of x converges, and it's possible to make a representation of a piecewise continuous function. Skip over some of this. All right, let's talk about some additional things concerning Fourier series. So basically in this section we'll talk about three different things. First of all is let's generalize from a period of 2 pi to a period of 2L for the function f. And then let's look at what happens if we have even versus odd functions. And then finally let's look at ways to expand limited functions into two different Fourier series. So basically the expression for the Fourier series changes if you have a period of 2L and the expression looks like this, where instead of a coefficient of n here we have n pi over L, which changes then the Euler formulas for the Fourier coefficients, now integrating from minus L to L, and our constant is 1 over 2L. Now I should mention here that you don't have to integrate from minus L to L. You could integrate from 0 to 2L. You could integrate from L to 3L. Your integration limits are not relevant because you're integrating over a period. So you can actually choose any period to integrate over. So here's an example of a periodic rectangular wave. Now, in this example, this function is what we would refer to as even, because f of minus x is equal to f of x. Here is an expression for the function. We have our expression for L. Notice L is 2. And so our period would be 4. So we can basically find a sub n by using our Fourier integral. And we'll end up with this expression. And then we can find, and remember a sub n is the coefficient of the cosine function. And then, I'm sorry, the coefficient of the sine function. A sub 0 will come out to be k over 2 if you do that integral. Now, and I think I said that wrong. So a sub n is the coefficient of the cosine function. So now, if n is even, notice that a sub n vanishes, and if n is odd, it does not vanish. So you end up with only non-zero values for n equals 1, 5, 9, and so on. You get 2k over n pi. You get minus 2k over n pi for 3, 7, 11, and so on. So this is fairly common to have these kind of patterns. So if we take these coefficients and we substitute that back, we see that we get a constant term plus a series of cosine functions. Now, because this function is even and the cosine function is even, the only way you can build a function like this out of sinusoidal terms is to have cosine functions only. If there were any sinusoidal terms, they would introduce an odd aspect to the function, which would make it impossible to have an even function. So we know, looking at this, that we'll only have cosine functions in this series. We also know that we'll have a constant term in a sub 0 because this function is not symmetric about the f of x equals 0 axis. So in effect, it has a DC-like term that would have to be present in order to represent this periodic wave. We can do a change of scale, and notice this wave is shifted around, so it now has an amplitude of k, still has a period of 4. Basically, by introducing this shift in x and introducing this magnitude of k, we do a couple things. This k shows up here, but because we shifted it, we now have an odd function. And so our odd function is going to give us sinusoidal terms. So by introducing shifts, you can basically change a function from an even function to an odd function. Not always, but it can be done. So if we have an even function that we know is an even function where f of minus x is equal to f of x, then we can write that as a series of cosine terms only. If we have an odd function, we can write that as a series of sine terms only. So There's a basic theorem that says the Fourier coefficients of a sum, f1 plus f2, are the sums of the coefficients of f1 and the coefficients of f2. And this obeys linear multiplication, so the coefficients of some constant times f is that constant times the corresponding Fourier coefficients of f. So that makes an interesting thing possible. Here is a function, basically, that's a single triangular wave. And the interesting thing about this pulse, this triangular pulse, is that it can be resolved into two components. One that would be an even component, and the other that would be an odd component. And notice if you take figure A and figure B and you add those together, you would get effectively the original function back, because here we would have everything canceling out except this one part of the function from 0 to L. Now, we can't write a Fourier series on the function shown in figure 271, but we can write a Fourier series on the function shown in figure 272 because we have even and odd. So we could write a Fourier series expression for each one of these and then use the property that basically the actual function would be function at A minus function of B. And so we could take the difference in individual coefficients in order to get a Fourier expression for this figure here. So you can play some tricks mathematically, both with even and odd as well as with what is referred to as half-range expansions or extensions, an even extension and an odd extension, in order to trick the system into doing a Fourier analysis.